Hello everyone. So today we're going to start on for chapter 14. We only have the last two sections left. That will be 14.6 and 14.7. So chapter 14 is actually on what we call infinite series. So one of your favorite topic from BC Calculus, I'm sure. Section 14.1 to 14.5 are actually what you have learned already from BC Calculus. That's the reason why we're skipping them. But before we actually embark on what we need to learn about how to use infinite series to solve a differential equation, maybe we should review a little bit on what you have learned in BC Calculus first. So what we're going to talk about in today's video would be Taylor series. So what is Taylor series? So we call from BC Calculus, you have learned that we can actually approximate a function f of x near a center point, let's say x equal to x sub 0, by forming a Taylor series. And what does the Taylor series look like? The Taylor series will look like the following formula. The Taylor series will be the following: P of n, P sub n of x. This will be called n-degree Taylor polynomials. Will be f of x sub 0 plus f prime of x sub 0 times x minus x sub 0 plus f prime of x sub 0 over 2 factorial, or double prime, I'm sorry, x minus x sub 0 squared plus dot 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 plus f to the nth derivative at x sub 0 over n factorial x minus x sub 0 to the n. So this is called an n-degree Taylor polynomials. A Taylor series is basically limits, or well, maybe I would call it P of x, just basically equal to the limit as n approaches infinity, P sub n of x. Around x equal to x sub 0. So that's the formula for Taylor polynomials to nth degrees, and if we allow this process to go on indefinitely, we will have what we call the Taylor polynomials, a Taylor series. And of course, in actuality, we rarely be able to allow this process to go on forever. So most likely what we're going to do is we'll pick a sufficiently large n and stop right there, and would say that our function is Taylor polynomial is close enough to the Taylor series. And of course, you also probably remember learning that from BC Calculus, something called error bounds, which allow you to actually bounce the error and therefore allow you to know how big of error it is, how close your answer is. This Taylor polynomial can be written into a summation form, so maybe I'll write it this way. I'll just continue here. Will probably equal to summation k from limit n to infinity, summation k from 0 to n, f to the k factorial derivative of x sub 0 over k factorial x minus x sub 0 to the k power. So that would be your Taylor series formula. I don't know you remember how to do the Taylor series, so maybe we do one together right now. Here's our example. Let's say given the function f of x equal to 1 over 1 minus x, write the first, let's say first 4 terms of the Taylor series. Around x equal to 0. So to generate the first 4 terms, what I basically need would be the 0 derivative, 1 derivative, 2 derivative, and 3 derivative, provided none of them actually becomes 0. So let's go ahead and do that. So let's start with f of 0. F of 0 is 1 minus 0, which is just 1. So that one is easy. You know what? Actually, maybe I'll do this. I'm going to go and put on f of x first, which is 1 over 1 minus x, which actually I would write as 1 minus x to the negative 1. And then f of 0 will just become 1 minus 0 to negative 1, which is 1. Let's do f prime of x, so that would be negative 1 minus x to the negative 2 multiplied by negative 1, because that's a derivative of 1 minus x. So therefore, these two negative actually cancel out. So just become 1 minus x to the negative 2. So then f prime at 0 would just be positive 1 also. Then what happened to f double prime of x? So that would be negative 2, 1 minus x to the negative 3 times negative 1 again. So the negative actually cancel out again. So it become 2, 1 minus x to the negative 3. So f double prime of 0 would actually equal to 2. And I do need 4 terms, so I'm going to do one more term. So f triple prime of x, so that would equal to negative 6, 1 minus x to the negative 4 times negative 1. So once again, the negative cancel out. 6, 1 minus x to negative 4. F triple prime at 0 is equal to 6. So now I should be able to write out my power series and my polynomials. So p, if I say p sub 3, then that would be basically all these terms. So let's write this out. So p sub 3 of x would actually become 1 plus 1 times x plus 2 over 2 factorial x squared plus 6 over 3 factorial x to the third. And so p sub 3 of x actually equal to 1 plus x. Notice 2 over 2 factorial is just 1, so x squared. 6 over 3 factorial is also 1. So that's p sub 3. If I want the Taylor series, I have to represent it this way. And that's our Taylor series with the first 4 terms shown. Now here you can actually guess what the general term is. Even the question did not ask for it, but I would probably likely ask for that in your test. So the general term in this case seemed to me just x to the n. So therefore I can say that this is just a summation n from 0 to infinity x to the nth power. And that's what p sub x is, p of x is. Interesting thing to note is that what we have here for the power series is actually a geometric series. Note that this is a geometric series. A geometric series is when all the subsequent terms are multiplied by a common ratio, which in this case is x, and therefore imply that the interval of convergence should be anything between 1 and negative 1, because x is the common ratio. And for a geometric series, the common ratio have to be less than, absolute value of the common ratio have to be less than 1 in order for the series to converge. So therefore, the interval of convergence should be negative 1 to 1. Now, some things I want to show that are interesting about power series, but before I do that, I do need you to kind of know some of these common power series or common Taylor series. So these power series are very common that you should know, and they all kind of came from Taylor series. So the first one you should definitely know is e to the x, because we just used that in chapter 13.2. Which is 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus dot dot dot. And so the general term is just x to n over n factorial. And you can write that out as a summation. So summation, I guess n from 0 to infinity, x to n over n factorial. And you also should know the interval conversion, which in this case for y is actually from negative infinity to positive infinity. So if you have enough terms, you should be able to use this power series to generate the y to the x function almost completely. All right. So what are some other common power series that you should know? Well, you should ever know the next two also. That's the sine and the cosine power series. Sine is x minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the 7 over 7 factorial plus dot dot dot. The general term is just x to the 2n plus 1 over 2n plus 1 factorial plus dot dot dot. And the summation will actually be n from 0 to infinity. Because it's alternating, it's negative 1 to the n. Oh, that's actually what I miss here. Negative 1 to the n. Right there. You know what? I'm just going to take out the general term because I'm going to write that in the summation anyway. So if you want to see the general term, look at the summation. So negative 1 to the n, x to the n, 2n plus 1 over 2n plus 1 factorial. And the interval conversion for sine x is negative infinity to positive infinity. All right. Cosine x have a similar formula, but just using only even exponents. Oops, minus. So once again, I'm going to write out the general term into summation, and that's it. And the interval conversion for sine x is also negative infinity to positive infinity. So these three are probably the most popular power series that you should know. But I'm going to go and give you two more that you should know. The next one is tangent inverse of x, which is equal to x minus x to the third over 3 plus x to the fifth over 5 minus x to the 7 over 7 plus dot dot dot. So notice that that's actually very similar to the sine power series, but just without the factorial. So that will be n from 0 to infinity, negative 1 to n, x to 2n over 2n. X to 2n plus 1 over 2n plus 1. For tangent inverse, the interval conversion is only go from negative 1 to positive 1. And the last one is a natural log. But it's not natural log of x, but it's natural log 1 plus x. The reason why, because we cannot do the natural log of x power series, because when I plug in 0, it failed to exist. So the typical trick is to do 1 plus x instead. So when I do 1 plus x and center at 0, this would come out to be this. So similar to y to the x, but it's alternating and without the factorial. Also missing the 1, I guess. So this power series is actually a little tricky because it actually starts from, not from 0, but from 1 to infinity. Negative 1 to the n plus 1. X to the n over n. And this one also only convert between 1 and negative 1. But not include negative 1 because that would give 0 for the natural log. So these are some very common power series that you should know. So now let's show you some interesting thing about these power series. So first one that I want to show you, which we kind of see already in matrix exponential, is the fact that when you take the derivative of e to the x, you actually get e to the x. So let's say given that e to the x is equal to 1 plus x squared over 2 factorial plus x to the third over 3 factorial, show dx d over dx of e to the x is equal to e to the x, using the power series, of course. So let's go ahead and do that. So if I take the derivative of e to the x, I'm basically taking the derivative of its power series. And I'm just going to write one extra term, anticipating that when I take the derivative, one of the term would disappear. And when I take this derivative of this thing, I can basically just separate into taking the derivative of each term, because of the fact that differential operator is linear. And so when I take this derivative, the first term would just become 0 because it's constant. Derivative of x is 1. Derivative of x squared over 2 factorial is 2x over 2 factorial plus 3x squared over 3 factorial plus 4x to the third over 4 factorial plus ... Notice that the 0 go away, the 2 and the 2 factorial cancel out, the 3 and the 3 factorial turn into 2 factorial, 4 and the 4 factorial turn into 3 factorial, so on and so forth. And notice that the first term disappear. Now notice that if I look at the rest of the term, it just becomes 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus ... which is technically the exact same thing as the power series that we started with. And that's the reason why it's go back to e to the x. So I think that's pretty neat. So another interesting thing I can show is to show you why when I take the derivative of sine x, I get cosine x. And similarly, you can also try to take the derivative of cosine x and show that it's equal to negative sine x. But I'm going to just do the derivative of sine x instead. So let's say given sine x is equal to x minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the 7 over 7 factorial plus ... that's the summation n from 0 to infinity, negative 1 to the n, x to 2n, 2n plus 1 over 2n plus 1 factorial. Let's say we want to show that the derivative of sine x is cosine x using the power series. So let's go ahead and give it a try. So it's the same exact thing as we did before. I'm going to just try to take the derivative of sine x and see what happens. So that means I'm taking the derivative of the entire power series. So if I do that, then I'll just basically take the derivative of each term. I'm not going to write it out one more time. That's too much writing. So derivative of x is just 1. And derivative of 3x to the third is 3x squared over 3 factorial plus 5x to the fourth over 4 factorial minus 7x to the 6 over 7 factorial plus ... And so once again, the 3 cancel the 3 factorial, give you 2 factorial. 5 cancel, is a 4. Is a 5 factorial on the bottom. That's the reason why. 5 factorial. And with the 5 factorial becomes 4 factorial, and 7 with the 7 factorial becomes 6 factorial. So that just come out to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial plus dot dot dot. And so that clearly come out to be cosine x. Now, you could also actually look at it from the general term formula, so we can definitely give it a try. So if I do that, I'm basically taking the derivative of respect to x of the summation n from 0 to infinity, -1 to n, x to 2n plus 1 over 2n plus 1 factorial. So it might be a little hard to deal with this, but let's see if we can break it apart. So first thing is, the derivative can actually be moved inside our summation, because the summation is just sum of a whole bunch of terms, so I can basically take the derivative of each individual term and then add them up. Also, in this derivative, notice -1 to the n and 2n plus 1 factorial are both constant. Therefore, I can move them out of the differentiation. So therefore, it becomes this. Summation from n from 0 to 1, 0 to infinity, -1 to the n over 2n plus 1 factorial, derivative of x to the 2n plus 1. But that's the only part that have x in it. So if I do that, then what I have is the following, is summation n from 0 to infinity, -1 to the n over 2n plus 1 factorial. Derivative of x to 2n plus 1 become 2n plus 1 times x to 2n. So notice that the 2n plus 1 and the 2n plus 1 factorial cancel to just 2n factorial. And so therefore, after I take the derivative of this summation, I get the summation n from 0 to infinity, -1 to the n, x to the 2n over 2n factorial, and that is the same as cosine x. So that's pretty neat. The last thing I want to show you from today would be the following, is how to use a power series. So one way to use a power series is to basically try to use it to evaluate a function where we normally won't be able to evaluate any other way. And the reason why, because when I write it out into a power series, all I need to know is to know how to raise a number to a certain power, and then divide by some corresponding factorial, which are both things that we can actually do using basic add, subtract, multiply, and divide. But if we encounter a function that doesn't use those 4 basic operations, we're kind of stuck, and power series allow us to have that ability to approximate the value. So one of the most interesting things is to use a power series to approximate pi. So that will require us to use the tangent inverse. The only problem with using tangent inverse approximate pi is that you actually can find out is that tangent inverse actually converges to pi really slow. So therefore, meaning that you actually need a lot of terms in order to actually approximate pi accurately. So not a very good way to approximate pi, but it is one way to approximate pi regardless. So we're going to ask you to do this. Use this power series to approximate pi. So how do we do that? So when you make use of the following, we know that tangent of pi over 4 is equal to 1, which imply that tangent inverse of 1 should equal to pi over 4. And therefore imply that pi should equal to 4 times tangent inverse of 1. So now comes the big question. What is tangent inverse of 1? Well, I don't know exactly what that is, but I do have a power series that will allow me to figure it out. So therefore, this implies that pi should equal to 4 multiplied by 1 minus 1 over 3 plus 1 over 5 minus 1 over 7 plus dot dot dot. Notice I simply take the power series of tangent inverse of x and plug in 1 in place of x. Now let's see if we can actually try to approximate pi. So I'm going to do this. I'm going to approximate pi using maybe 10 terms. So normally, using 10 terms should give you a very good estimate. But remember I told you tangent inverse converges to pi relatively slow. So actually it's not going to give us a very good estimate at all. But we can definitely see what it is. So pi should be approximately equal to 4 multiplied by, I need 10 terms. So we're going to count out 10 terms. So that's 3. That's 4. That's 5. That's 6. That's 7. That's 8 is a minus right here. And 9. And voila, 10. So if you take out a calculator and just simply type that in and add it up, you should roughly have about 3.0418396189.3. So as you can see, it's not that close to pi actually, because pi is 3.14. Now, is there a way to actually calculate the error? Well, of course there is. The absolute error, in this case, should have to be less than 4 over 21. Imply that if I take pi and minus this approximation, it should be less than 4 over 21. Now you might be thinking, where did I get the 4 over 21 came from? Well, that's called alternating series error bounds. Alternating series error bound. Oh, I forgot the word series. Alternating series. Oops. Error bounds say that whatever error that you get, the error cannot be bigger than the next term in the series that you choose not to use. So in this case, the next term in the series that I choose not to use is the 1 over 21 term, but I have to multiply that by 4, so therefore it will be 4 over 21. That will be the error bounds. So if you simply subtract pi from your calculator with 3.041, oops, it's supposed to be 8. 3961893, you found that the difference between that and that should be less than 4 over 21, whatever 4 over 21 is. Alright, so these are all the things that I want to show you about power series and tangent series, kind of a reminder of what you have learned back in BC Calculus. So hopefully as we go through, as you're watching this video, you kind of remember some of these stuff from BC Calculus. Our next video, we actually go dive into how are we going to use this to solve a differential equation. Once again, we are actually not trying to solve the differential equation using this method, but use it to kind of form an approximation of what the solution should look like. More importantly, a Taylor polynomial of what the solution will look like. So we'll talk about that in our next video. Okay, talk to you guys then. Bye bye.